Now your browser knows the server. It knows the machine, it knows the port. But now comes the real game. How does your data actually travel? When you send a message, open a website, or watch a video, does the whole thing travel as one big file? No. The internet cuts your data into tiny pieces. These pieces are called packets. But here's the important part. Sending packets is not enough. They also need a delivery style. Some data must arrive perfectly. Some data must arrive quickly. And this is exactly why we have TCP and UDP.
A packet is a small piece of data with delivery information attached to it. Think of it like a small envelope. Inside the packet, there is a piece of the actual data. And outside the packet, there is information like where it came from, where it is going, and which service it should reach. Instead of sending one huge block of data, computers send many small packets across the network. Breaking data into packets makes the internet more flexible. Packets can move through different routers. They can travel across different paths. If something goes wrong, only a small part may need to be sent again. This is much better than trying to send one giant file in one piece. So whether you are loading a web page, sending a message, or watching a video, under the hood, packets are moving. But now we have a new problem. If data is broken into packets, how should those packets be delivered? Should every packet arrive correctly? Should missing packets be sent again? Should packets arrive in order? Or should we prioritize speed, even if some packets are lost? This is where TCP and UDP come in.
TCP and UDP are transport protocols. That means they define how data is delivered between your computer and a server. They both help move packets from one place to another, but they have very different priorities. TCP focuses on reliability. UDP focuses on speed and low overhead. Here is the simplest mental model. TCP is like a reliable delivery service. It checks that the data arrives, keeps things in order, and can resend missing pieces. UDP is like sending quick messages without waiting for confirmation. It is faster and lighter, but it does not guarantee that every packet arrives. This difference is the heart of TCP versus UDP. TCP is used when correctness matters. It tries to make sure the data arrives. It keeps packets in the correct order. And if a packet is lost, TCP can request that it be sent again. This makes TCP very useful for things like websites, logins, file downloads, payments, and APIs. In these cases, missing or corrupted data would be a serious problem. Imagine downloading a file. If one packet is missing, the final file could become broken. That is not acceptable. So TCP tracks the packets. If packet number 5 is missing, TCP can detect that and ask for it again. Only when the pieces arrive correctly can the full data be rebuilt. That is why TCP is reliable. Before TCP sends actual data, it first creates a connection. This is commonly called the TCP handshake. The client and server agree that they are ready to communicate. You can think of it like saying, "Are you there?" "Yes, I am here." "Okay, let's talk." This setup adds a little delay, but it helps create a reliable connection. TCP gives reliability, but that reliability has a cost. It needs connection setup. It tracks packets. It handles ordering. It resends missing data. All of this adds overhead. So TCP is excellent when accuracy matters more than raw speed. But for some applications, waiting for missing packets can actually make the experience worse. That is where UDP becomes useful. UDP is much simpler than TCP. It sends packets without creating a full, reliable connection first. It does not guarantee delivery. It does not guarantee order, and it does not automatically resend missing packets. Because of this, UDP has less overhead. That makes it useful when speed matters more than perfect reliability. Think about a live video call. If one packet arrives too late, it may no longer be useful.
You do not want the call to freeze just to wait for one old packet. It is better to continue with the latest audio and video. That is why many real-time applications prefer UDP or UDP-based protocols. They care more about staying live than perfectly recovering every missing packet. Online games are another good example. In a fast game, your position changes many times per second. If one old update is lost, it may be better to ignore it and use the newest update instead. Waiting for old packets can create lag, so games often use UDP because speed and low latency are more important than perfect delivery of every single update. So here is the basic comparison. TCP is reliable, ordered, and can resend lost packets. UDP is faster, lighter, and does not guarantee delivery. TCP is like carefully sending a package and confirming it arrived. UDP is like quickly throwing messages across the network and moving on. Neither one is always better. They are designed for different use cases. TCP is commonly used when data must arrive correctly. Websites often use TCP. APIs usually use TCP. Logins, file downloads, email, payments, and banking systems need reliability. You do not want missing pieces when sending money, logging into an account, or downloading important files. That is why TCP is used in many everyday internet activities. UDP is commonly used when speed is more important than perfect delivery. Video calls, voice chat, online gaming, and some live streaming systems often use UDP or UDP-based protocols. DNS also commonly uses UDP because DNS queries are small and need to be fast. If something fails, the client can usually ask again. So UDP is useful when low latency matters. A common beginner mistake is thinking UDP is bad because it does not guarantee delivery. That is not true. UDP is not bad. It is just designed for a different purpose. TCP is not always better either. If you need reliability, TCP is a great choice. But if you need speed, low latency, or real-time communication, UDP may be the better choice. The right protocol depends on the problem. For websites, traditional HTTP usually runs on top of TCP. That means when your browser loads a normal HTTPS website, TCP is often involved underneath. But modern web technology has also evolved. HTTP 3 uses a newer protocol called QUIC, which runs over UDP. We do not need to go deep into that now. For this video, the important idea is TCP and UDP are lower-level delivery methods that other protocols can build on top of. Now, let's connect this with everything we learned so far. DNS helps find the IP address. The IP address finds the machine. The port finds the service inside that machine. And TCP or UDP defines how packets are delivered between your computer and that service. This gives us a much clearer picture of how internet communication works. For example, when you open a website using HTTPS, DNS first finds the IP address. Then your browser connects to the server using port 443. Underneath, TCP usually helps deliver packets reliably. That reliability matters because your browser needs correct data to display the page properly. If important pieces are missing, the page may not load correctly. Now, compare that with a video call. In a live conversation, low latency matters a lot. If a small packet is lost, it may be better to skip it and continue. Waiting for old data could make the call feel frozen or delayed. That is why real-time communication often uses UDP or UDP-based protocols. The goal is to keep the experience live and responsive. Let's recap. Data does not travel as one big file. It is broken into packets. TCP delivers those packets carefully. It focuses on reliability, order, and correctness. UDP delivers packets quickly. It focuses on speed, simplicity, and low latency. Both are important, and both power different parts of the internet. Now we know how data can be transported between your computer and a server, but there is still one important question. Once the connection exists, how does the browser actually ask for a web page? How does it say, give me this page, send me this image, or return this API data? That is where HTTP comes in, and that is what we will explore in the next video.